let us start with decoding the column design in Etabs. So you will definitely agree with me that one of the most tricky element to design in Etabs is a column element. We will see the reasons why I am calling it tricky, and that is why most of the people, they don't have the confidence to design the columns in Etabs, and then they go to other software for designing. That is, they will do the analysis in Etabs, and then they will go for design in RCDC or some other software. But I'm sure that once you see the decoding of column design in Etabs, your confidence of designing column in Etabs is definitely going to increase. I'm sure about it. So let us start with the design of column. So the first type that we are going to study is the ordinary column design, and that we will do manually first of all. Now, when I say that my column is ordinary, so for the sake of this workshop, we mean that it is a column uh, in a structure which is being designed only for gravity load. Okay, there are no earthquake loads in that model. So we will design the model only for gravity load, and that's why our column will be designed only for gravity load. Now, these type of building, when we say that there is no earthquake load, so definitely these are buildings which are, say, of lower number of stories, or they are in mild seismic zones, and that's why we can design them without earthquake as well. So let us first study the calculation of the ordinary column, which will be designed only for gravity load. So similar to what we did yesterday, we selected one random column, which is the column on story 4, grid 4 and B. This column we have selected. We extracted the results of that column. So I'll just show you that column in our actual Etabs model. So since it is ordinary, I will select our model for gravity loads only. Yeah. So this was the model that we prepared for the workshop. And the column that we are selecting is when we go to story 4 and grid 4 and grid B. So this is the column that we have selected for study in our Etabs. Someone is asking me recording permission. Okay. So this is the column that we will use for our design. So let me show you how I have extracted the results. So I will select the perspective toggle view from here, and I will go here. I will select only this column and click on show selected objects only. I am intentionally keeping the grid on just for reference. Now, combination, obviously 1.5 dead load live load, because we are designing it for gravity loads only. And say I want to see the bending moment first of all. So I'll just right click on that column. 1.5 dead load being a column, first of all, I am interested in looking at the axial force. So this is the value of the axial force that we are getting from the analysis, 4673 kilonewton. Let us just confirm it, that whether we have taken the same value in our presentation. Yeah, 4673 kilonewton. Then I will go to major bending moment. Here you can see that the shear force is 24.75, that is 25 kilonewton. This is similar to what we got yesterday in no, sorry, we haven't seen ordinary column yesterday. Yeah, so the shear force is 25 kilonewton and the bending moment is 42.32 kilonewton in the major direction. So major moment is 42. So yes, major moment is 42 and the shear is the same. And now let us see the minor shear and minor moment. Minor shear is 28 and minor moment is 48. This is similar to what we have taken for the study. 47, that is approximately 48, and 27. So this is how we have extracted the results for the ordinary column. I'll go back to the presentation again. Yeah. So these are the forces that we got from our analysis. Our minor direction bending moment is 47.96. That is approximately 48. And the major moment is 42. And axial force is 4673. So yes, these are the values that we have taken for our study. Axial force, minor axis moment, and the major axis moment. Now, first of all, we will design the column for flexure. Size of the column is 300 by 900. All the columns are of the same size. Concrete and steel again is the same, M30 and Fe 500. Now, let us pay attention to this value, which is effective depth D. Now, whenever you want to check your column manually, actually I was coming to this point yesterday, but then I realized that it is not valid for beam. In case of a beam, we directly give the input of the effective cover, right? But in case of column, if you recall that whenever we are defining any column, that time we don't give Etabs the effective cover, we give the clear cover, right? I will just go to the definition of my column. So this is the column. And here if you see in reinforcement, then the input that we give to Etabs here is the clear cover for confinement bars. So how Etabs is calculating the effective depth or say effective width using the clear cover. So most of the people have this misconception that whatever is the data below the tab of clear cover, this data is required only when we go for reinforcement to be checked. But let me clear it, my friends. This data, even though the number of bars and everything is not valid when we are designing the column in Etabs, but the diameter of the bar that you select is important when it calculates the effective depth or effective width of the column. That is, if I say that my clear cover is 40, then it will add the diameter of the confinement bar 10 to it, which is taken from the definition. So here, if you give the bar dia say 20, 25, some odd figure, then your calculations will not match and they are not correct. And this is the diameter of the confinement bar, that is stirrup, and this is the diameter of your longitudinal bar, which is 20. So then here it will be 20 divided by 2 and it comes out to be 60 mm. Okay. So here if you are giving any random bar size and you expect Etabs to calculate the effective cover correctly, then it is not a wrong, then it's not a right thing to do. You have to specify the bar diameter correctly. It is advisable to go for higher bar dia size if you are not sure what you are going to get from the design, so that you will be on the conservative side. So this is what I wanted to show you yesterday, that in the definition itself, the diameter of the stirrup and the diameter of the main bar is important, because it will calculate effective depth from that in. Yeah. So then Etabs calculated our effective depth as 60 mm. The effective cover as 60 mm, and hence my effective depth is 840 mm. Now the manual calculations will match with the design results of Etabs. Otherwise, they will not match. Now, let us go to the next part of manual design, which is calculation of minimum eccentricity. Now, when we were looking at the concrete frame design preferences or overrides, if I may not recall it correctly, we had one tab of calculate minimum eccentricity. And I told you yesterday that this tab is not important for beams. It is required only in case of columns. So now let us see how it is used in the design of the columns. So if you go to IS 456-2000 page number 42, it clearly states that all columns shall be designed for minimum eccentricity equal to unsupported length of column divided by 500 plus lateral dimension divided by 30 subjected to a minimum value of 20 mm, and wherever biaxial bending is considered, it is sufficient to ensure that eccentricity exceeds the minimum about one axis at a time. So the code is saying that you can consider minimum eccentricity about one axis at a time. There is no need to consider it about both the axis simultaneously. You can consider it about one axis at a time, and the formula works out to be unsupported length divided by 500 plus whatever is your lateral dimension in which you are calculating the eccentricity divided by 30. But in no case it should be lesser than 20 mm. So unsupported length in our case will be the story height minus the depth of the beam in the story above. Okay, so 3600 minus 600 divided by 500 plus 300 divided by 30, because we are calculating the minimum eccentricity about minor axis right now. So if you work out this, it comes out to be 16 mm, which is less than 20 mm. So we will stick to the value of 20 mm. Now this is the value of minimum eccentricity, 20 mm. Then what will be the value of bending moment due to minimum eccentricity? It is nothing but the value of your axial force P into E minimum. Okay. So our axial force is 4673 kilonewton. So 4673 into 0.020 in meter. So our minimum eccentricity about minor axis will be 93 kilonewton meter. Similarly, if you calculate the minimum eccentricity about the major axis, considering the dimension as 900, rest everything remains the same, you end up in the value of minimum eccentricity as 36 mm, which is the minimum eccentricity along major axis. Hence, the bending moment due to minimum eccentricity along major axis will be same, the axial force into the value of eccentricity 0.036, and that comes out to be 168 kilonewton meter. Okay, so our minimum eccentricity along minor axis is 93 and along major axis it is 168. Now let us go ahead in the manual calculations. Yeah, so now comes the most important part in column design, which is nothing but the calculation of effective length. Okay, this is the only reason why people find the design of columns tricky in Etabs or in say any software. Okay, because somehow unfortunately we are not taught this in a correct manner in our academics itself, and that is why people face a lot of problem when they start practice in structural engineering. So let us try to understand the effective length calculation, but in our presentation this effective length calculation will be explained in two parts. Okay, so in the first ordinary calculation I am keeping it simple. I am directly assuming the type of my frame. Okay, I'll show you what is the type of the frame. So I am directly assuming the type of my frame to be non-sway. But when we go to the ductile design, at that time we will once again go through that how the framing type should be selected. Now, for ordinary frame, that is frame without earthquake, let us assume that the frame is non-sway. Okay, there is no sway in my frame. I'm just assuming it. And because there are no lateral loads in my model. So if you go to SP24 Appendix D on page number 150, they have given a very nice diagram of what do you mean by a non-sway frame and what do you mean by a sway frame. Now, for all those for whom these terms are new, they need to pay attention. And in case if you don't understand it during the presentation, you can ask me doubt afterwards, and you can also go and study this concept later on. So it is very, very important to classify your framing type, whether it is a non-sway frame or it is a sway frame. So when I say that my frame is non-sway, it behaves something like this, which is shown on the slide in the left bottom corner. This is the diagram of a non-sway frame, and here this is the diagram of a sway frame. Now, what is creating problem in case of a sway frame is that if you see, the column itself is not in a straight line. Okay, there is certain amount of deflection in the frame itself in the horizontal direction, because of which the P force will not come in straight line up to the footing. Instead of that, it will be P plus some additional moment, which is equal to P into delta. This is the bending moment due to eccentricity in the behavior of the frame itself. But if you see the sway frame, this point of application of load and this footing, they are almost in straight line. Only the column is bending, but the line is straight over. But here there is delta. So this frame is a sway frame. Now, for those who don't know what is the concept of sway and non-sway, for them I'm just explaining you in very simple terms that your frame will be converted from non-sway to sway when your lateral load resisting elements, that is your shear wall or your beam column frame, does not have sufficient strength to withstand the lateral load. It is not going to fail, but the amount of deflection, the deflection due to lateral load, will be somehow higher than what we get in a sway frame, than what we get in a non-sway frame. So in this sway frame, due to your lateral load resisting elements being weak, you will get higher amount of lateral deflections, and as a result, you have to consider the effect of this P delta in your design. But if your frame elements are strong enough to resist the lateral load, there will still be deflections due to lateral load, but they are not significant enough to consider in your design. When it is a sway frame, it is mandatory for you to consider the effect of this delta. But if that delta itself is negligible, you can ignore that additional bending moment of P delta and perform your design considering it as non-sway. So I hope so that you got the concept of sway and non-sway. Now let us see that how do we determine whether the frame is sway or non-sway. Right now I am just going to show you where it is given. Okay, the exact details we will study when we go to our ductile column. So these details of whether your frame is in the sway category or in the non-sway category, how to determine that is clearly given in your IS 456-2000 Annexure E. If you go to Annexure E, it is giving you some calculations to classify your frame into the category of sway or non-sway. Yeah. So this is your Annexure E, effective length of columns, and there is some formula given of Q, and it says that if this Q value is less than or equal to 0.04, it is a no sway frame, otherwise it is a sway frame. So we are going to come to this part of the code, but we will study it in detail when we go to the ductile design of columns. So right now I am straight away assuming that my frame is a non-sway frame, just to keep the calculation simple. but later on you will definitely get an idea. So if you go to IS 456-2000, page number 42, effective length of compression member, which is nothing but our column, in the absence of more exact analysis, the effective length LEF of columns may be obtained in annexure E. So we have to find out the effective length of the column using annexure E, whether it is a sway frame or it is a non-sway frame. For both the types, the effective length has to be determined using annexure E. Okay. Now, many people, what they do is they calculate the effective length using these tables. You will see this quite often. Even I guess in our academics itself, we use this table for finding out the effective length of compression members, but it gives you approximate results. The results are not exact. That is why the code is asking you to use annexure E for calculating the effective length of the column. Here, if you see, it is clearly given E3. For normal usage, assuming idealized conditions, the effective length of column in a given plane may be assessed using table 28, which is nothing but this table. But these results are approximate, and even Etabs does not calculate it using table 28. Etabs is also calculating it using these graphs given. Okay, so now let us see what are these graphs. So basically what we have is one factor called as beta 1 along the y-axis and one factor called as beta 2 along the x-axis. So using these two factors, beta 1 and beta 2, we can find out the effective length of our column, right? We can come from here and here and we will get the value of effective length factor K. Now, in this annexure E, there are two tables. One, or you can say figure, there are two figures. One is figure 26, which is for column in a frame with no sway. So this is the figure to be used for a column which is, or a frame which is in the category of non-sway, right? So this is what we are going to use right now. This is the figure when your framing type is non-sway. Now, if you go to the page below, there is one more figure given, very similar, same beta 1 and beta 2 factor on the x and y axis, but now this figure is for a frame, for a column in a frame without restraint against sway. So this is basically the figure for a framing type which is sway. Okay, so figure 27 is for a sway frame and figure 26 is for a non-sway frame. Now, just to give you an idea, or just to give you the feel of what exactly is different in these two figures, if you have understood the concept of non-sway, we know that obviously in a non-sway frame, the effective length of our column will be smaller as compared to a sway frame, because in sway frame, our frame is weak somehow, and that is why it is going larger lateral deflections. So obviously you are going to get higher effective length factor if your framing type is sway. So if you see this table in detail, in your table for non-sway frame, the effective length factor, it starts from a value of 0.5. It is starting from a value of 0.5, and the maximum value that you get is 1.0. So your effective length will be in this range only, 0.5 to 1. when your framing type is non-sway. But if you go to the next figure, here your starting point of effective length calculation itself is 1, and the extreme point, that is the maximum value, is infinity. And this infinity, my friends, is the biggest problem when you design column in Etabs. If your effective length factor, or say your beta 1 and beta 2 is somewhere in the range beyond 0.9 and 1, the effective length factor, it jumps from 5 to directly infinity. I have seen people using models where the effective length factor is 20, 10, in this range. But it is, you have to use that factor after understanding the proper concept. Okay. So the thing to note here is that in a sway frame, your effective length factor will be greater than 1, and it can go up to infinity. But if it is a non-sway frame, the maximum limit is 1. Okay. So this is the difference between non-sway and sway, and you can categorize your frame as sway or non-sway using this factor Q. It will tell you, this Q will tell you whether you should use figure 26 or 27. So for the sake of simplicity right now, we have assumed since we don't have earthquake load in our frame, and I am assuming that my frame of beam column is strong enough that it will put my structure into a non-sway category. So I will, just for the sake of simplicity, we will proceed with non-sway type of the frame when we are designing ordinary column. Yeah. So as we saw in that table, then it is to use that figure 26 right now for non-sway column, it is first of all important to find out the factor beta 1 and beta 2, because this beta 1 and beta 2 are going to give us the value of effective length factor K. So this beta 1 and beta 2 are given to us in annexure E itself, in the same annex. In figures 26 and 27, beta 1 and beta 2 are equal to summation of Kc divided by summation of Kc plus summation of Kb. So summation Kc is nothing but the flexural stiffness of column, and summation Kb is nothing but the flexural stiffness of beam. So beta 1 and beta 2 is summation of Kc divided by summation of Kc plus Kb at the top and bottom ends of the column. So at the top it would be beta 1, at the top end of the column it would be beta 1, and at the bottom end of the column it will be beta 2. Now if you see any column, say this is one column, and there are beams framing into that column at one story, and then there are beams framing into that column at the lower story. So when we say beta 1, it is basically calculated using the stiffness of column at this junction, where the stiffness of the beams will be of this level. This level beams will be considered in the calculation of summation Kb. Okay. And this junction will be used in the calculation of beta 2. So the sizes or the data of beams at the lower story or the bottom end of the corner will be used in the calculation of beta 2. Now if you take the example of our model, in which the size of the column is uniform throughout the height of the building, and the size of the beam is also uniform, so you can also say that beta 1 will be equal to beta 2 in our case, because we have modeled beams of uniform size throughout the project. That is why our beta 1 will be equal to beta 2. Okay. So this is the formula for beta 1 and beta 2. It is nothing but summation Kc divided by summation Kc plus Kb. Now, even if I am right, even most of the practicing consultants or the people who are in the industry since long, they calculate this factor beta 1 and beta 2 incorrectly. I will tell you why they calculate it incorrectly. Because unfortunately, in our IS 456 2000 Annexure E, nowhere in the entire code they have given how to calculate summation KB. You cannot calculate summation KB directly using our basic analysis theory, because this value of summation Kc divided by summation Kc plus summation Kb, this equation was given to us in the Wood's theory. This equation or this chart or this figure 26 and 27, these are derived from Wood's theory. But nowhere in the annexure they are telling you how to find out the value of summation KB. My team has had to do a lot of research to find this value of KB correctly and to give you a proper reference of KB. To give you the proper reference, they had to study a lot of literature, and ultimately SP24 came to our help once again. If you refer SP24 Appendix D, now SP24 is basically based upon our earlier version of IS 456, but the effective length calculation is unchanged. So we can refer that SP24 when we are calculating the value of summation KB. So please note down SP24 Appendix D gives you the calculation of summation KB. So it says that while using the charts in figure 23 and 24, now in IS 45627, we have figure 26 and 27. But in the earlier version of the code, it was figure 23 and 24, but the figure is the same. While using the charts in figure 23 and 24 of the code, following points should be kept in view. For braced frames, okay, braced frames means your non-sway frame, the frame which is not going to undergo a high lateral deformation. For braced frames, beam stiffness KB should be modified as 1/2 into I by L. Okay, so if you recall our basic analysis theory, flexural stiffness of any element is given by a value EI by L. If you can recall it, it is given by EI by L. Flexural stiffness we used to denote it by K. Flexural stiffness K is always equal to EI by L. But if you refer to this equation, here we have 1K in the numerator and another 2Ks in the denominator. So we can take the factor E outside, which is nothing but the modulus of elasticity, concrete EC, and they will cancel out each other. Okay, so right now for us, K value is equal to I by L only, right? Flexural stiffness K is equal to I by L. But my dear friends, Mr. Woods is asking us that whenever you are calculating beta 1 and beta 2 for using this figure 26 and 27, the KB, that is the flexural stiffness of beam, should be modified to the value of 1/2 I by L, which is nothing but 0.5 into I by L. So we are directly reducing the stiffness of our beam to half if it is a non-sway frame. For braced frames, beam stiffness KB should be modified as 1/2 into I/L. Now, why this factor is 1.2? That you have to study the Wood's theory in detail. But right now we are only showing you that where exactly this value of KB is given. So for non-sway frame, KB will be equal to 1/2 I/L, and in unbraced frames means your sway frame, this frame. In unbraced frames, the beams are bent in double curvature. That's why I have intentionally added this diagram of the frame in the PPT. If you see this bending of the column. This column is bending in double curvature. This column is bending in single curvature. That's why the beam stiffness in such frames, that is sway frames, has to be modified as 1.5 into I/L. So in our non-sway frame, we were reducing the stiffness of our beam to half, where here we are increasing our beam stiffness to a factor of 1.5. Now, from where these factors have come, that you need to study the Wood's theory, but the correct calculation of KB is to be done as per Appendix D, SP24, page number 152. Otherwise, my friends, your manual calculation of stability index Q or your classification of a frame into sway and non-sway will never match with what Etabs is calculating. And Etabs is considering SP24 Appendix D while calculating this stiffness factor KB, and this we have proved in our manual calculations, which will be shown ahead. So I hope so that this concept of calculation of beta 1 and beta 2 is clear. Beta 1 and beta 2 are required for finding out effective length factor K. So now, and this is given in the Wood's theory. There is a very wonderful explanation of the entire effective length calculation using these two figures in SP24 Appendix D. You can definitely go and refer it later on.
Welcome you all in ISO certified live training program, Etabs, RCDC and Excel that makes you a professional structural engineer. In this training program, you will learn everything about Etabs and RCDC from basic to advanced, real life project of medium rise structure from architecture plan to final design sheet, real life project of high rise structure with all advanced topics, design of structural elements using advanced Excel sheets. Have a look over the features of this training. Daily live classes conducted by expert for 1.5 hours. Recording of every session with lifetime access. Can interact with expert anytime, 24/7. Exposure to real practice. ISO certification of training completion. It's 5-star rated training program. Till now, more than 1,000 participants have benefited from this training program. Now you are the next. Hello everyone, welcome you all in a new ISO certified live training program, design of substructure using CSI Safe, Excel and manual. In this training program, you will learn all about the concept of substructure design, commands in CSI Safe software for the substructure design, validation of CSI Safe result with your manual and advanced Excel sheets. This training program will cover 4 real life projects. In the first and second, we will cover all the types of isolated foundation in CSI Safe software. In the third real life project, we will cover the raft foundation. And in the fourth real life project, there will be the coverage of pile and pile cap design of basement wall, and at the end of this training program you will learn how to prepare the final design sheet for the site execution. Have a look over the features of this training. Daily live classes conducted by expert. Recording of every session. Can interact with expert anytime. Exposure to real practice. ISO certification of training. It's 5-star rated training program. Till now, more than 1,000 participants have benefited from this training program. Now you are the next.